Hello. Please find your seat if you haven't. We have plenty of seats here. We'll start soon. It's get ready.
Get ready.
Yeah. We are going to have an exciting talk. So. Yeah. Ladies and gentlemen, it's really my honor to introduce Professor Yiming Yang, an expert in information retrieval and machine learning at Carnegie Mellon University. Okay. 25 years ago, I was this lucky PhD student sitting in the classroom, information retrieval, I see. 25 years ago, I know you at that time. I was this lucky PhD student sitting in the information retrieval class, co-taught by Professor Yiming Yang and my advisor, Jamie Callan, two SIGIR Academy members, right? They introduced us to the beauty of IR. And I also get to know Professor Yiming Yang. And Professor Yang truly embodies the spirits of my heart is in the work. Because she's always available to her students. And she's often the last person to leave the lab. I know that because I work hard. I leave lab at 10 p.m. And she's still there, right? And her vision, dedication, and all the hard work give her the nickname of fearless pioneer in the field among her PhD students. Right? And I have learned much from her, both academically, also about life. I still remember in 2010, Geneva, she told me she has made a very impactful contribution in the field of text classification, information retrieval, and more recently, large-scale language models like a very famous model, XLNet, and also work on reasoning with graph neural networks, large language model RAG, and so on and so forth. She has a lot to share. Let's welcome Professor Yiming Yang.
Hi, thank you for the warm introduction. I'm truly honored to give this talk. And it's always nice to hear what the students say about you, in front of you, and behind you. So I hope it's all good. Okay, let me start my talk. So let me start with a piece of personal memory. I presented my first SIGIR paper in 1993, and I saw Dr. Sultan right in front of me in the front row of the audience. So I asked ChatGPT to generate a picture about this scenario, given my short description like this, presenting my SIGIR paper in 1993, with Dr. Sultan sitting in the first row of the audience. Essentially, ChatGPT cannot directly generate an image, but instead it generates a detailed description, which is necessary to use to ask GPT-4 to produce the image. So here is the detailed description produced by ChatGPT. Imagine a conference room with a podium at the front. You are standing in the podium, at the podium, presenting your paper. The audience is seated in rows of chairs facing you. In the first row, there is Dr. Jared Sultan, a prominent figure in the field of information retrieval, listening attentively. The room is filled with professionals and researchers, blah, blah, blah. So you can see that the ChatGPT generated scenario is quite close to what we have nowadays. And so this is a picture I got generated by GPT-4. It's actually quite close to what I have in mind, except the presenter is a male. So then I asked the system to correct it by a young female. That is what I get. So you can still, maybe when I was young, maybe that's kind of flattering. But you still can complain that the slides does not look like SIGIR relevant. But nonetheless, I was quite amazed about what the system can do nowadays. Recall that in traditional IR, we only focused on text-based matching between queries and documents. But nowadays, the system can do a lot more. It understands your goal based on a very short description, and it's quite knowledgeable to figure out the necessary details for accomplishing your goal. And it calls a powerful module to perform text-to-image mapping. And it can also correct itself based on cross-module feedback. So a few decades ago, we couldn't have imagined such a system, or even just a few years ago. So what are the technological advancements behind? A major one, I think, is representation learning and reasoning with neural networks. And this will be the central theme of my talk today. In traditional IR, we relied on a backwards model or presentation for document under the word independence assumption. We all know that is incorrect, but we use that anyway for convenience for decades. But nowadays, in dense retrieval, we focus on neural network-based learning about contextualized, task-oriented, and knowledge-enhanced embeddings of words, documents, queries, and all kinds of variables in complex settings, where large language models have played important roles in the bigger paradigm shift. So I picked a few pieces of our relevant work as examples in our journey in this direction. Let me start with the first one, the two-tower pre-training for large-scale language dense retrieval. So again, in traditional IR, we relied on the inverted indexing for efficient computation of the query document similarities at the inference time. However, such a technology is no longer applicable to dense retrieval when we focus on BERT-style cross-attention model, which remove the word independence assumption by performing deep embedding of queries and documents. But it's also raised a significant challenge for scaling up. That is, it requires expensive computation for online embedding of both queries and documents. So we address this challenge by proposing the two-tower transformer model. So these slides compare two neural network architectures side by side. On the left, we have the BERT-style cross-attention model, which takes the concatenation of query tokens and document tokens as the input. After multi-layer embedding of those tokens, it aggregates all the embedded vectors into a single vector as the representation of the query document pair. And this vector is further converted to a scalar as the system predicted relevance score of the document given the query. You can see that all the computation is done after the query is given. That means significant computational burden at the inference time. On the right, we have the two-tower model. That is, we have the query tower and the document tower for the embedding of query and document respectively. However, we can still use a BERT-style encoder, but we can train these two towers independently. That is, we can use pre-computing for document embedding and online computing for query embedding to substantially reduce the inference time. For example, with 1 million of documents and 1,000 queries, the two-tower approach took about a few hundred CPU milliseconds, while the BERT-style cross-attention model took a few hours of CPU time. I should mention the same idea was proposed by another research team, namely the dense passage retrieval model. Apparently, this is an important design choice for scale-up dense retrieval. We also studied the pre-training strategies to train the proposed model. A naive approach is just to use a BERT module as is, that is language modeling trained on free text. A better choice, or a more preferable choice, is to train the system with a large collection of relevant query document pairs, if available. However, we do not want to rely on extensive human annotation. Instead, we can use automatically extracted pseudo-relevant query document pairs, where the pairs can be extracted from online documents, such as Wikipedia pages. So we developed several strategies for collecting such training pairs. Strategy number one is like this. Given a passage, randomly select a sentence from the passage as the query, and treat the remaining part of the passage as the pseudo-relevant document. Strategy number two is like this. Given a Wikipedia page, randomly select a sentence from the first section as the query, and randomly select a passage from the remaining part of the same page as a pseudo-relevant document. Strategy number three is the query part is the same as in the previous strategy, while for the document part, we randomly pick a passage from another page which has a hyperlink to the query page. We examined all the three strategies and found the joint use of all of them produces the best results. And here is our training objective. That is, we want to maximize the quantity, that is the summation of the log likelihood of each document given a query for each query document pair in the training set. And here, the conditional probability of a document given a query is defined using a softmax function. So here are our evaluation results in passage ranking given a query. The performance metric is recall at top k in the ranked list for k equal 1, 5, 10, 50, and 100. The green bars are the results of BM25, representing the best of the traditional IR models. And the orange bars are these BERT-style transformer model that trained with the masked language modeling. And interestingly, the deep embedding of queries and documents by the BERT-style model does not necessarily improve the performance over BM25, especially on the low recall and the high precision regions. And the red bars are the results of the backwards model, where the term weighting is automatically optimized with a multilayer perceptron, where the training data is exactly the same pseudo-relevant query document pairs, which we used to train our proposed approach. That is which has the blue bars. If you compare the blue bars with the red bars, you can see clearly the blue bars substantially outperform the red bar. Means that although both methods using the same training data, but the deep embedding by the transformer style model substitutional backwards representation. So in short, large language model-based contextualized embeddings for queries and documents have successfully addressed the fundamental limitation of traditional backwards models, essentially by removing the word independence assumption. However, naive pre-training strategies such as the BERT-style masked language modeling may not be good enough. The proposed two-tower transformer model with better training strategies apparently are both scalable and substantially outperforming the other strong baselines. So my next topic is on active retrieval augmented generation, or active RAG in short. As a hot topic in the intersection between large language models and dense retrieval, there's so many papers published on RAG. So I asked the ChatGPT to generate a gist summary about the most recent trends. And here's a summary. And the red part is marked by myself for some important keywords, such as adaptive retrieval augmentation, dynamic retrieval frameworks, and those are exactly the primary focus in our active RAG paper. We observed that early RAG has been focused on single-time retrieval. But here we focus on an iterative process with sequentially generated queries during the generation of a long document by a language model. The key research question is, of course, how to decide when and what to retrieve, or in other words, how do we generate queries in context. So here we show a concrete example to illustrate the process. Consider that the input X is generate a summary about Joe Biden. And we treat the input as the initial query and use the retrieved passage D sub X as the input to the language model, which produces the first piece of the output Y sub 1 as Joe Biden attended blah. Here, the system detected that the blah part is rather uncertain, meaning that the token level probabilities are below some pre-specified threshold. So at this point, the system generates the next query, Q sub 2, searching for the university Joe Biden attended. And based on the retrieved passages, the system generated the language model generated the next piece of output Y sub 2 as the University of Pennsylvania, where he earned blah. Again, the system detected the blah part is rather uncertain, so the system generated the next query, Q sub 3, searching for the degree that Joe Biden obtained. And finally, the system produced the Y sub 3 as a law degree. At this point, all the token level probabilities are above the pre-specified threshold, so the process stops. For query formulation, we have two kinds, namely implicit queries versus explicit queries. So given the output on the top line, where the uncertain parts marked with an underline, the implicit query is just to mask off those uncertain parts. And the explicit query is generated by a language model module, such as ChatGPT, that asking about each of the uncertain parts given its context, such as what university did Joe Biden attend, and so on. So here are our evaluation results in open domain question answering. And we have 5 benchmark data sets here. And the blue bars are the results of the language model-based QA system without retrieval. And the red bar is with a single-time retrieval of the same QA system. And the yellow bars are the results of the QA system with a multi-round of retrieval, where the queries are generated with a naive strategy. That is using the previous window of a few tokens as the next query. And the green bars are the results of our proposed active RAG methods. So in short, and what to retrieve is still an open challenge in RAG in a dynamic setting. So far, the query generation in our proposed approach is based on self-detected token-level uncertainty. For future work, we can extend the metric to mitigate diverse types of hallucinations, such as the lack of supporting evidence locally or globally, undesirable biases, self-contradiction issues, and so on. That is, we want to support multi-aspect RAG in dynamic settings. Another important direction is to support multimodal modal RAG, combining the retrieved information from multi-sources, including text, images, tabular data, figures, knowledge graphs, and so on. So the next topic is about scalable oversight of large language models with easy-to-hard generalization. So this is our recent paper archived and still under review. The key research question is, can AI systems still be improved when their capability surpass those of human supervisors? And our answer is yes, especially with the easy-to-hard generalization approach we proposed in the paper. Here is the famous scenario I downloaded from the recent OpenAI paper in the end of last year. And essentially, it's trying to illustrate what is a scalable oversight challenge. On the left is the nowadays, when the AI agents or machine learning trained models getting more and more capable and powerful, that they can be more knowledgeable and more correct than human supervisors. And then the crucial question is, can we still develop better AI systems under this condition? And in other words, addressing this challenge is crucial for the true success of a future AI system. The OpenAI paper proposed an approach they called our analogy, namely the weak to strong generalization analogy, which is different from what we're proposing. Here are the slides. I compare the two analogies side by side. On the left is the OpenAI's analogy, and on the right is our analogy. So in the weak to strong analogy, the question they focus on is like this. Can we use a task-oriented small language model to teach a general purpose large language model so that the student model can outperform the teacher model on this specific task? And the answer in that paper, if you look at their empirical results, I would say is inconclusive. That means it works sometimes, but not always. And in our paper, we focus on different question. That is, can we use labeled data on easy tasks to obtain a language model for solving harder tasks for which we don't have human supervision? And our answer is yes, and we provide strong evidence in the domain of solving mathematical problems at different levels. So here, let me show the training process in our proposed approach. And we have two kinds of training data, namely easy data versus hard data. And the easy part consists of math problems and solutions with different levels of difficulty. And we have a human annotation about whether an answer is correct or wrong given the problem. And the hard data, we only have the hard problems, but we don't have the answers and nor have a human annotation of the answers. So we use the easy data to train two kinds of modules. One is the language model generator responsible for a given problem in natural language and provide the solutions for that math problem. And the evaluator is essentially a binary classifier judging whether a given pair of problems are correct or not, and with some confidence scores. So using the easy data to train both modules, and after the training, we can use them to generate pseudo-labeled cases for the hard problems. For example, when given a problem, hard problem to the trained generator, and it can produce a bunch of candidate answers, and the evaluator provide the likelihood scores or confidence scores, and for the binary decisions, judging the answer is correct or wrong. So now we have the pseudo-labeled, and based on those scores, then we select the most likely final answer. So now this process gives us the pseudo-labeled hard case training examples, and using those additional data, we can further fine-tune the language model generator using some kind of reinforcement learning techniques. So this is the training process. And after the models are both trained and fine-tuned, further fine-tuned, we can just follow this path to generate the final answer. And recall that this sampling process and the selection process could be costly. So a shortcut is just directly use the trained generator with greedy decoding for the final answer. So basically, you have control between this to balance or to trade off this efficiency and effectiveness here. Maybe you want to ask the intuition behind. That is why it should work. Why should we only have labeled training data on easy tasks and to solve harder problems, or to train a model which is capable to solve harder problems? So intuitively, a math proof is an easier task than providing the proof from scratch. Also, we know that in classical computer science, a solution of an NP-hard problem can be verified in polynomial time. That is, again, validation is an easier task than finding the optimal solution itself. So therefore, a model trained on easy problems could serve a good or sufficiently good evaluator for judging the predicted solutions on harder cases. So the evaluator produces the scores, for example, can, on harder cases, allow us to perform weighted voting over the candidate pool, or to select the best out of n as the final answer. And the evaluator produces the pseudo-labels over hard cases can provide additional training data with useful training signals to further fine-tune the generator. So this is our rationale behind the proposed approach. So here are some our main results. So we trained the lemma 7b on the easy data. And 7b means 7 billion of model parameters. And we evaluate this our approach on hard cases. And the graph, the horizontal axis, is the size of a candidate sample pool ranging from 1 to 1,024. And the vertical axis is the percentage of problems being correctly solved. And we have 3 curves, means 3 different voting strategies, including majority voting, or weighted voting, or best of n. So all the 3 curves suggest some kind of performance trend, although their exact value can differ from each other. And we have the yellow dashed line as the generator trained only on easy data with greedy reading, greedy decoding. So you can see, as long as the sample pool is sufficiently large, for example, larger than 10 candidates, and all these voting strategies can substantially outperform the baseline performance. We also compared to another baseline, which is the dashed black line, which we use not only the easy data, labeled easy data for training, we also leveraged the hard case with human annotation for training, but with a only greedy decoding of the trained model. So altogether, it shows that the sampling-based voting strategies can substantially improve the performance, supporting our initial rationale for the proposed approach. Here, we show some ceiling performance after training an even larger language model, Lemma 34B. Again, we trained on the human annotation on easy data. So now the evaluation is on all math problems. That means from level 1 to 5. And the ceiling performance is achieved by the weighted voting. Weighted voting methods and the sample size of 1,024. So essentially, we got roughly 52.5% of the problem being correctly solved. How that compared to GPT-4 or Gemini Ultra, and actually it's very close to the other state-of-art methods. Recall that all these reference methods are using huge amount of human annotation, but our system only have human annotation on easy 1,024 solutions, and use the evaluator to score and rank all of them for their final selecting final decision. So this means the computational cost will be 1,000 to 2,000 times large compared to the supervised fine-tuning with a greedy readout. Of course, we still can accelerate the computation with the parallel computing, but nonetheless, the price is, so the performance improvement does not come for free. So in summary, I believe the generalization. Although we only focused on the math domain, but the basic idea or approach, pseudo-relevance feedback in traditional IR, and transductive classification and boosting and bagging in early machine learning approaches. So in other words, we are just visiting similar ideas in the new context of neural network-based learning. And I take the chance to share an exciting piece of news. We just, in the AI Mathematical Olympiad Challenge, which ended by the end of June, there were over 1,100 teams participating, and our team ranked number 2 in the competition. And both, it's mainly just my students and some summer interns work. So we're all very impressed. We were impressed by how much language models nowadays can do in solving pretty hard math problems. So lastly, I just wanted to briefly introduce our some adventure with neural network-based learning beyond the text, that is, in solving NP-complete problems. So many of us have a computer science background, and we all know that NP-complete is the hardcore of computer science. Here, I'm not trying to prove if a P equals NP. Then instead, I'm more interested in how can we use cutting-edge neural network technologies to better solve NP-complete problems that a traditional approach and previous machine learning methods failed to solve. So let us to have to look at a couple of examples of NP-complete problems. TSP stands for traveling salesman problem. The task is to find a tour in a given graph where each node is visited once and only once. and in the closed tour. And we want to find the tour with the minimum traveling cost. MIS stands for maximum independent set. And the task is that given a graph, and we want to find the maximum subset of mutually independent nodes. So in this shows the same graph with the red spots defined identified set. You can see the solutions in the middle panel have the subset independent set size of 4, so which is better than the solutions on the left and on the right. So how this kind of problems have anything to do with the neural network-based learning? So here is some connections. And most of the NP-complete problems can be defined as a search problem over a graph for some optimal solution. And a candidate solution can be generated by sequentially selecting a variable, which can be a node or an edge in the graph, and we select them one at a time under certain constraints. So this reminds us about the generative process of language modeling and graph neural networks. By the way, I didn't have much time to talk about graph neural networks, but which is a hot topic in recent machine learning, and we are pretty active in that direction. So given that insight, we have successfully developed several state-of-the-art neural network solvers for some NP-complete problems. For example, by the early part of the year 2022, all the machine learning-based approaches could only scale to TSP problems in the graphs with 100 nodes or less. So this kind of situation put all the machine learning methods in a disadvantageous solution compared to existing exact solvers in classic computer science, because when those exact solvers can scale to the problem size, they are guaranteed to find the optimal solution. But the machine learning-based methods, it does not guarantee that. They only solve the problem by approximation. So in other words, unless the machine learning methods can scale to problems much larger than the existing classical solvers, then there's no chance for the machine learning-based method to beat the exact solvers. So in later of that year, we developed a method called the DIMES, which is a reinforcement learning-based neural network solver, a graph neural network solver, which is scaled to TSP graphs with 10,000 nodes, and produced the best results on evaluation benchmarks. And for those kind of larger problems, the traditional exact solvers failed to scale up. So a few months later, we developed another method called the Diffusco, which is the first graph-based diffusion model for solving NP-complete problems. Diffusco further outperformed DIMES, both in scalability and accuracy. Technically, we have many design choices. For example, to use autoregressive language modeling or to use non-autoregressive language modeling, or use encoder-decoder architecture or encoder-only architecture, and also about how to use graph neural networks to obtain node embedding and edge embedding, and how to use those embeddings to guide the search strategy through reinforcement learning or to train the policy gradient to focus on the most promising solution to avoid exhaustive search. And also involved with how do we adapt the recent success in computer vision with continuous vector spaces to the discrete vector spaces for graph-based machine learning. And so I will skip all these technical details. The main point I want to make is that cutting-edge language modeling and graph neural networks are indeed applicable to combinatorial optimization. So, and in other words, those techniques are not only powerful for natural languages, but it's also applicable to many challenging problems in formal languages. And this is a promising direction for future research, in my opinion, with potentially huge impact, both theoretically and practically. One may think that NP-complete is only of the interest in theoretical computer science. But if you think about how Amazon deliver their shopping product over the world, then we have zillions of traveling salesmen's problem as the version of the traveling sales problem. That is, we have many salesmen to solve the delivery problems called routing problems. So we also did many other relevant work I did not have a chance to cover in my talk today, including XLNet, known as the permutation language modeling, and graph neural networks with NP-complete problems, like mixed integer linear programming or integer quadratic programming. And more details you can find from our reference list. So I will stop here for questions and comments.